Recall that we said that a distribution was a list of probabilities assigned to each of the possible values of a random variable. So far, we've looked at discrete probability distributions. In this session, we're going to spend some time with a very important continuous distribution, the normal distribution. Then we'll take a brief look at three other distributions that often come up in statistics. The normal distribution is a symmetric, bell-shaped continuous distribution characterized by its mean and its standard deviation. We use the Greek letter mu to symbolize the mean, and the Greek letter sigma to symbolize the standard deviation. The normal distribution has a characteristic shape, but that shape can be shifted and stretched by adjusting the mean and the standard deviation. The normal distribution looks like this. Things in nature often, but certainly not always, tend to be normally distributed because the normal distribution results when you add up a bunch of little random effects. Have you ever seen Plinko from the game show The Price is Right? A contestant stands at the top of a large board with a bunch of pegs on it and releases a disc. The disc goes bouncing down the board. At each peg, the disc can either bounce left or right randomly. As those lefts and rights add up, you get most discs landing in the center, and the proportion of discs that lands in any given spot drops off as the landing point is farther away from the release point. If you played Plinko many times and plotted how often the disc landed in each spot, you would start to see something that resembles a normal distribution. This idea of a normal distribution resulting from adding up a bunch of little random effects is behind something called the central limit theorem, an incredibly useful and important force behind much of statistical inference. We'll talk more about the central limit theorem next week. There's a special name for a normal distribution with a mean of 0 and a standard deviation of 1. It's called the standard normal distribution. If a random variable has a normal distribution with some mean and standard deviation, then its z-score has a standard normal distribution. But note that not all z-scores are going to be normally distributed. The z-score is only normally distributed if the original variable was normally distributed. Remember that standardized scores, z-scores, are computed by subtracting the mean and dividing by the standard deviation. Once you've subtracted the mean of a bunch of standardized scores will be 0. And once you've divided by the standard deviation of a bunch of standardized scores will be 1. The standardized score shows where an observation is relative to its distribution, and thus allows comparison of observations from different distributions by putting them on the same scale, the relative to its distribution scale. As a standardized score for the family of normal distributions, the standard normal distribution is like the mother distribution. You can get all other normal distributions from the standard normal distribution by stretching, that is changing the standard deviation or the scale, and shifting, that is changing the mean or the location. As I mentioned earlier, finding probabilities for continuous probability distributions requires calculus and is related to the area underneath the distribution curve. In practice, people usually use software or a table to look up probabilities from the standard normal distribution. We'll talk about how to use the standard normal table to find three kinds of probabilities from the normal distribution: left-tail probabilities, right-tail probabilities, and middle range probabilities. Since we'll be looking up the probabilities from the standard normal distribution, the first step in finding a normal distribution probability is always to compute the z-score. You have to do this first before you proceed. Let's first look at how to find a left-tail probability. This is the probability that some normally distributed random variable z is less than some specific value, little z. It's this region here on the left, the probabilities of all of the possible values that are less than z. Left-tail probabilities you can look up directly from the table because the table shows all of the left-tail probabilities. You use the rows to find the ones and the tenths digit, and then you find the column for the hundredths place. Let's find the probability that a standard normally distributed variable z is less than negative 2.25. First we find the row for negative 2.2, and then we find the column for 0.05. And the value in that row and column is the probability that z is less than negative 2.25. In this case, the probability is 0.0122. So the probability that z is less than negative 2.25 is about 1%. Suppose that an energy company did a study and found that household use of electricity had a mean of 673 kilowatt hours and a standard deviation of 556 kilowatt hours. Suppose that the distribution was normal. Let's find the percentage of homes that use less than 500 kilowatt hours. Well, the first step is always to compute a z-score. So we take the value that we're looking for, 500, and we subtract the mean, which is 673, and we divide by the standard deviation, which is 556. This gives us a z-score of negative 0.31. Now we can find the probability that z is less than negative 0.31. We look it up in the table, and we find that the probability is 0.3783, or 38%. The percentage of homes that use less than 500 kilowatt hours was about 38%. Next, instead of talking about left tail probabilities, we can talk about right tail probabilities. This is the probability that a normally distributed variable z is greater than some value, little z. So it's the probability that z is any of these values that's greater than little z, here on the right. Now we know that the whole distribution has to add up to 1, so that's the area under the entire curve. But the table only shows left tail probabilities. So if we want to find this area here on the right, we can take 1 and subtract away the left tail probability that corresponds to this section over here on the left. What's left is the blue region that we're looking for. Now, due to the symmetry of the normal distribution, it so happens that the right tail probability is the same as a left tail probability when the sign is flipped. That is, the probability that z is greater than a little z is equal to the probability that z is less than negative little z. So another way to find the right tail probability is to take the opposite of the value we're looking for and then look it up in the left tail probability table. A World Health Organization study of the health in various countries reported that in Canada, systolic blood pressure readings have a mean of 121 and a standard deviation of 16. A reading above 140 is considered to be high blood pressure. So suppose that the systolic blood pressure in Canada has a normal distribution. What proportion of Canadians suffer from high blood pressure? Well, first we always compute the z-score. So we take 140 and we subtract the mean, 121, and divide by 16, which is the standard deviation. That gives us a z-score of 1.19. Now we can find the probability that a standard normally distributed variable is greater than 1.19. Recall that the way we do this is we find the left tail probability for 1.19 and then subtract that from 1. So let's look up in the table what the left tail probability for 1.19 is. It's 0.8830. So we can subtract that from 1 and we get 0.117. That is to say, about 12% of Canadians would have high blood pressure. Now remember, another way we could do this is to take the opposite of the value we're looking for and find that value's left tail probability. So instead of looking up 1.19, we could look up negative 1.19, and we find that that's the probability we're looking for, about 12%. Finally, the middle range probability is the probability that some normally distributed variable is in the range between A and B. We can find this probability by subtracting the left tail probability of A from the left tail probability of B. Let's take a look at how that works. The blue shaded region here is the left tail probability of B. It's the probability that some normally distributed random variable is less than B. The red region here is the left tail probability of A. That is to say, the probability that some normally distributed variable is less than A. What we want is what's left over when we take the blue region and subtract away the red region. That gives us our middle range probability, the probability that z is between A and B. We took the left tail probability of B and subtracted the left tail probability of A. What's left over is what we're looking for. Going back to our blood pressure example, what proportion of Canadians have a systolic blood pressure in the range from 100 to 140? Here A is 100 and B is 140. Well, first we calculate the z-scores for A and B. We take 100, subtract the mean, divide by the standard deviation, and that gives us negative 1.31. We do the same for B, which is what we had just done before, where we found 1.19. Now we can look up in the table the left tail probabilities for A and B. Probability that a normally distributed variable is less than 1.19 is 0.8830, which is what we found before. And the probability that a standard normally distributed variable is less than negative 1.31 is 0.0951. So we subtract those, and what's left over is the probability that the normally distributed variable is between A and B. So we get about 79%. 79% of Canadians would have a blood pressure in the range of 100 to 140. When computing different kinds of probability, it's really a great idea to draw a sketch and to highlight the region that corresponds with the probability you're trying to find. Often in statistical inference, we'll be interested in looking at things from the other way around. Instead of having a particular value and asking what its tail probability is, we'll have some probability and ask ourselves, how big does this variable have to be in order to achieve this tail probability? These special values that fit with specific tail probabilities are called critical values. A critical value is the value of a random variable that corresponds with a specified tail probability. For example, we could ask what value of z gives the left tail probability of 0.025. What's the critical value for 0.025? Instead of finding a particular row and column, we'll search the table for the value of the probability that we're looking for, 0.025, and then we'll look to see, well, what row and column does it fit in? Here's the value of 0.025 in the table. We see that it's in the row for negative 1.9, and it's in the column for 0.06. So the critical value for a probability of 0.025 is negative 1.96. Finally, there are three other distributions that we'll come across when we talk about statistical inference in the second half of the course. We're going to look at them only briefly, since we usually are only interested in their critical values. The first is the t-distribution. This is used for z-scores of normally distributed variables when the standard deviation used to compute the z-score is an estimate and not the true value. Just like the normal distribution was characterized by a mean and a standard deviation, the t-distribution is characterized by something called the degrees of freedom. It's related to the number of observations that was used in the estimate of the standard deviation. The specifics of how that works aren't important. The only thing that's important here is to know that for a t-distribution, you'll have to know what the degrees of freedom are. Second, we have the chi-squared distribution. The chi-squared distribution results when you add together the squares of several standard normally distributed variables. It's also characterized by something called the degrees of freedom, and in this case it's the number of variables that you added together to get the chi-squared variable. Finally, there's the F distribution. The F distribution is a ratio of two chi-squared variables. If you have two variables that are distributed with the chi-squared distributions, and you divide one by the other, the new variable that you get is going to have an F distribution. It's characterized by two degrees of freedom, a number of degrees of freedom for the numerator and a number of degrees of freedom for the denominator. Each of these distributions has its own table of probabilities that can be used to find left, right, and middle range probabilities, as well as critical values, just in the same way as with the standard normal distribution. We'll discuss how these distributions are used in statistics when we get into statistical inference.